so we talked about this for a little bit. Talking about, okay?
Oh, okay.
Right there. So that's the discriminant. That's the definition. That's going to help us a lot because that's what's under the radical. That's what matters to tell me about the roots. We went into that. Let's take a look at this one. So when we plug this into our program, the two roots that we get in the discriminant. Go ahead, Mar.
So the two roots are negative 2.15 goes to 8.
So give me just the nearest, maybe 2 decimals for now.
All right. Negative 2.35.
Okay. And
0.85.
that's a U in the beginning there. I agree. Now, you noticed, and you were saying, which I think you were saying it for a reason, that went on forever, right? Is that what you were pointing out?
I mean, it doesn't show it, but they're just.
Is there a dot, or is it actually terminated on your calculator?
I think it's terminated.
I'm curious, who has an 83? Or you have terminating? Is yours a dot, or terminating?
I'm trying to set mine up. I did a different program. I did a different program.
Okay.
So I'm just trying. I
Trying to
took
program it
a
in.
picture of the screen yesterday,
Okay.
so I'm just doing.
And I have it on Moodle too, I think. I don't know this one. Maybe financial, okay?
Yeah, I don't know like if something's wrong with your program.
I mean, something's definitely wrong with the program, yeah. Yesterday, we get some answers from over? Can I see it?
My calculator might be like dying.
No, I think it's just not in there.
Yeah.
It's alright, so your battery's actually dead. So look on with something for now. Okay, we'll let it down. We can look at the programs together if you want. Did everybody else say this values? Anybody have any 83s? Everyone have an 84 at this point in time. Everyone has an 84, oh my gosh. Regina, get that program in. I want to see what you get. You have an 83. I have an 83 also. Doesn't the same calculator really. But I'm curious if there's dots when you get answers or if there's not.
Yeah, you said.
So let me point something out. This did not tell me anything about whether or not we have an irrational root. Because if I just write these numbers down, those look rational to me. A terminating decimal is rational. I know you guys are doing the program, but just listen for a second, okay? A terminating decimal is a rational number. But these answers are irrational. How do we know this? Who did the discriminant? What's the discriminant turn out to be?
41.
41. And that means you're going to have a square root of 41 in the quadratic formula. When the discriminant is 41, it's going to be negative b plus or minus the square root of the discriminant all over 2a. So these are our roots right there. These are clearly irrational roots. The calculator doesn't always tell me that it's irrational because it's showing all those decimals and you might think it terminates. Good chances are that if you see enough decimals to fill the screen of the calculator, ready? The answer is irrational. If you see enough decimals, then there's no repeated pattern. If you see 66666, right? Then it's 2/3. 0.666 repeating forever in a calculator, and maybe a 7 at the end. That's what 2/3 is. So certain decimals repeat forever, and they'll show up like 0.222 repeating is 2/9. You know that trick, by the way? 0.1 repeating is 1/9. 0.2 repeating is 2/9. 0.3 repeating is 3/9. 0.4 repeating is 4/9. They're all 9s. And those digits repeat. Anyhow, so you can have rational answers showing up with a lot of decimals, but if you see what you see now, look at your screen, do you see any point where there's a repeat in the pattern? A serious repeat where it happens forever? You might see a repeat in the very beginning, but does it go on forever is the question. Anything? In there, no? Yeah, so it's an irrational answer. Again, because the discriminant is root 40, but the discriminant is 41. And therefore we get a root 41 in our answer. Alex?
How do you find the root of discriminant?
B squared minus 4AC. Remember I added it to my program at the end yesterday? So Julia did as well. So her screen just shows that the word, look, discriminant equals 41. She added it to the program. Remember during the class I was adding it to the program? That's what I was doing. So you can do that, or you can honestly, Alex, look, B squared minus 4AC. It's 9 minus 4 times negative 2 times, you know what I mean? Okay, so it's 9 minus negative 40. Not 9 minus negative 40, it's 9 minus negative 32. 9 minus negative 32 is really 9 plus 32, which is really 41. Okay?
So just the b squared.
Correct. Again, and that's from the previous slide, Alex. So let's take a look at the. Let's draw ourselves an XY axis. These are my roots, or solutions to the equation, or x-intercepts if it were written as a function. So these are my x-intercepts. So let's graph them. Let's just put a dot at negative 2.35, I'm estimating, obviously. And put a dot around 1. Okay, this graph has x-intercepts in those locations. So either it looks like this, or it looks like this. You don't have to know this yet, but I know some of you do. Anybody know what indicates whether the parabola opens up or opens down?
Okay, I don't know. But like if the first sign is like if A is negative or positive, then
That's it, exactly. When A is positive, it opens up. In this case, A is negative, so it actually opens down. And we don't have to worry about graphing it, but we're going to do it in a section or two. So I might as well show you this so you can see already. So this is going to look something like that. So we see the two roots are at the two x-intercepts, the u values. On the next example, though, as Julia was talking about, the discriminant in the previous one was 41. Okay, so I should have noted those. So that's a 41. Next example, again, calculator program, let's do it. You can practice by hand, obviously, but I'd rather honestly just use the calculator program to do it. We did it, we might as well use it, right?
I would, but
I know. And if I had more batteries next door, I'd get them for you. I don't have any left. I do usually have some, actually.
I got -3 for both of them.
-3 for both of them. So the x-intercepts, or the zeros of the function, right, mean to do this. And we got -3 for both. Now, would I really write it twice? No. But for the sake of today, I'm going to write it twice, just to emphasize the fact that this is a double root. We have two roots, but we have one singularity in that sense here, that there's only one actual root, and it's a double root. There technically are two roots to this polynomial. Why are there two roots to the polynomial? Because it's
squared.
It's squared. But I want to talk about something that we're going to see in the next coming sections. I want to just allude to something. You want to make a point or your question? Okay?
So when you have a parabola, it like goes over the x-intercept twice, so that means that you have to have two roots, or most of the time.
Most of the time, yes. So let's talk about what Julia is saying right now. Let's pause for a second. Let's think back to the last example. I could even go back for a second. I'm going to go back for a quick second. We have a repeated answer. So there's only actually one x-intercept, and it's at -3. How is that possible? How is that possible to only have one x-intercept? Did you know?
Thank you for the previous question.
Okay, hold on one second. I do want to see that. It's not? Okay. That's what I was wondering. Maura, how do I know? What do I see on this graph?
Discriminant 0.
Discriminant 0. So when the discriminant 0, we have a repeated root. Good. But why? How can we only have one x-intercept? How's that possible? Is my question.
Would it be just like straight down and straight up? What would
Not straight down and straight up. The root is the vertex of the parabola, or the top, either one, right? It's the vertex. It's the max or the min. In this case, A is positive. Look at the A value, it's 2. If A is positive, it opens up. So this is going to be the minimum of the actual parabola. A repeated root shows up as a point of tangency. Alex, Helen, you know the word tangency, both, right? Geometry or took. For those that don't know the word tangency, you know the word tangent, it's the same thing. A tangent to a circle is this. When I take the pencil and it touches the outside of the circle once, right, like that. Well, look at the curve. When a curve touches a straight line once, it's called a point of tangency, or a tangent point. Let's jot that down there so you know that terminology. Okay, it's a tangent point, or a point of tangency. Very useful word for calculus. Okay, I like to throw the vocabulary out there that you're going to see later on. Let's take a look at this one. I should have noted it. Sorry. The discriminant here was 0. That's a 0 there. This one. Roots. Roots. Let's do the program for this one. And you should all please practice this. I know it's simple, obviously, because it's right in front of you, but just do it to practice so you get it right.
Wait, so when you say roots of the equation, do you mean solve the discriminant or like the entire thing?
So when it says find the roots, it means use the quadratic formula or use the program. But then it says note the value of the discriminant. So afterward, we want to note it. So and then this one will do the same thing. Okay, so in example 1, the discriminant was 41. In example 2, the discriminant was 0. And now our example 3, what's the discriminant and what are the roots? Alex, give me something.
The roots are
The
1
roots?
minus
Okay.
1 minus 8.1 repeating, or like it just goes on for a while. It's I.
Okay. 1 minus 8.1i.
Yeah, and then the other one
They should be the
It's
same.
0.8.
Oh, 0.8, okay.
Yeah.
But it's plus or minus pretty much, right?
Yeah.
Okay. But 0.81, gotcha. What is the discriminant here, please? What is the discriminant here?
Negative 24.
Okay, so clearly the negative, as Helen told us earlier, gives us imaginary or complex numbers as roots. Complex results. Now, root 0.81 is probably also irrational. Did this go on forever with no possible pattern, or was there a pattern?
It didn't go on forever because you could see the eye, but it was just the
But
one.
was there any pattern in it at all?
No.
Any pattern? How many decimals did it give you? The whole screen? So that means it's actually going on forever. So unfortunately, so my program on the computer I showed you yesterday showed ... which I actually like. Because it indicates that it goes on. I don't know why they dropped that from the 84. All of your calculators aren't showing ... right? So unfortunately, it's not going to show that. But it seems like this is going to go on forever with no repeated pattern. And the reason I know that, look, the discriminant is not a perfect square. So it's got to be irrational. If this were 25 as a negative, right, if this were negative 25, we would have a 5i right here, right? We'd have a 5i. Yes.
It doesn't. Mine doesn't show ...
It does not, right? Yeah, so none of them seem to be showing it.
It does when it repeats, but for this one, like if you do one where it like comes out repeating, it will show ...
So repeating shows ... now, and the ones that don't?
I don't know. But like we did one yesterday and it showed ... But like this one, it doesn't show. Because remember the I was like cut off.
We'll try one with an answer of 1/3 as a root. Let's do that on purpose. We'll do that. I'll show you. We'll see if it's a repeating or not. Because I don't remember from yesterday. Mine showed it for everything. Even when it was irrational, it showed ... Whereas yours are not showing that right now, and these are irrational.
I thought if you could see the eye, rational.
You don't even, it's not, it's not any of yours now, right? Okay, it's root. You don't even see
I
the
thought,
I.
like, because if you can't see the eye, then it's irrational because it's going on and eyes at the end, but you can see the eye on the screen.
On your screen, you can see it?
Yes.
So don't rely on your program to show you irrational or not. Rely on the discriminant. So it's
Yeah.
good to note that and the program. I like that we added the word discriminant at the end of the program and it reads it out. Because if the discriminant is not a perfect square, so 25 would work, 36 would work, even if they're negative, it works, right? So even if it's negative 25, negative 36, it makes the answer rational at least. Not rational, but it makes it not a radical in the answer is what I'm saying.
I figured out why. It was because I have it on A plus BI instead of real numbers.
Well, A plus BI is what it should be on, or else it's not going to show you imaginary roots. It's going to say error, non-real answer. If you try that one again, the same one, it's not going to give you the I. It's going to say error, non-real answer. That's what we ran, right? Did we run into that yesterday? You have to put it in A plus BI form so that when the answers are imaginary, it actually shows up as imaginary answers.
Yeah.
So unfortunately, we're kind of stuck in A plus BI form. Anyhow, we'll see what happens with that. But what I want to talk about here again is the concept that the program is just giving you an estimation of what you're doing. So you have to recognize that the discriminant is what's telling you a lot about the problem, right? The discriminant itself. Let me see what the other ones turn out to be before I get into more. Okay, so before I get into the next example, let's open up a blank slide. Let's FOIL this out real quick. Let me see what this comes out to be, and then we're going to use the quadratic program for this one. So this will be 2x squared, outer give me 4x, inner is 3, that's 7x plus 6. All right, let's use this, please. Notice what I'm doing on purpose. I'm making the problem on purpose so that the root will be, oh, that's going to be 3.5. Switch to 3. Oh, crap. I screwed up. Sorry. This should be switched. These should be switched. Right? Because when I solve this, I want the answer to be 2/3 is what I'm saying. So I want to subtract the 2 and then divide by 3. So that's going to change my answers here. Hold on. And this is going to be a 4 in the end. So we're going to have 3x squared. Then it's going to be 6x and 2x is 8x. And then a 4 at the end. So that will work. I put the 2 and the 3 in opposite spots. I did this on purpose. So let's see what the roots are for this, please. On your calculator, run the program. And tell me if you get ... or not. And tell me what it works out to be and what it shows up as. And I'd like to hear both calculator versions. What do you have for yours?
Negative 0.666, and then I got -2.
What does it say at the end, though? Is it ... or it says 7? So it does 6s for a while until it gets to 7, and it shows the 7. So there's no dots. Okay. Regina, yours?
Same thing.
Same exact thing? Okay. So good to know that it's not going to show that. That's interesting. And then the other one is just going to be -2, right? What about for an imaginary one? Let's see. I'd have to make that work. I got to think of one for imaginary. It's not. I can't just make the factors work this time. I'll come back to that one, and we'll do an imaginary to see how it works with I. Anyhow, obviously, don't let the program fool you, right? Don't let it fool you. So we have 3 types of cases here we just talked about. The discriminant can be negative, it can be 0, or it can be positive. When the discriminant's negative, our roots are complex conjugates, i.e. imaginary. Okay, and we get 2 of them. In the case that it's 0, we get 1 real repeated root. And in the case that it's positive, we've seen that we're getting 2, we're going to say distinct, different. Distinct roots. And the positive case has 2 subcategories, right? And Helen pointed these out for us earlier. If it's a perfect square, the roots are rational. If it's a non-perfect square, the roots are irrational. That's a subcategory of the positive case. So if I have a discriminant of 49, I get rational roots. And they're real, and they're distinct, and they're 2 of them. But if it's the square root of 48, unfortunately, those roots are going to be irrational. And when they're irrational, we call them binomial. We've seen this term already. Oops. Conjugates. Okay, binomial conjugates. It'd be like 3 plus or minus root 7 as an answer for the roots. Okay, they're always going to come in pairs. They're always going to come in pairs when they're irrational or when they're imaginary. They're either complex conjugates when they're imaginary or binomial conjugates when they're rational. But when they are rational roots or when the discriminant is 0 and it's a repeated root, we're not going to have to worry about conjugates in those cases. Okay, so conjugates are key. Maybe let's underline those in yellow. Okay? In these 2 cases, we have 4 cases. Negative, 0, positive perfect square, positive non-perfect square. Those 2 cases have conjugates. Again, positive non-perfect square or negative roots or negative discriminants yield conjugates. One of them being binomial, one of them being complex. Let's take a look at a little bit more challenging problems now. Okay, now that we've categorized. So example 4 asks us about this equation. And unfortunately, though, we don't know the A and the C values here. We're told that A is K and C is 4K, where K is some number. We don't know what K is. K could be 0, K could be 2, 3, 4. But either way, A is whatever K is, and C is 4 times whatever K is. Now, we know the following. We want to find the values of K that creates an equation with the following characteristics. First, a double root, then 2 different real roots, and then finally, imaginary roots. When do we get a double root? What is the case when we get a double root?
When it's 0.
When what is 0?
Or like
Not when K is 0.
C is 0.
Not when C is 0. Very good. When the discriminant equals 0. So for part A, we need to set the discriminant equal to 0. You might be saying right now, how is that going to help? How is that going to help? We can answer that. How is this going to help us? Find the value of K. It's the whole gist of the problem. Find the value of K. You started it. You said, no, go for it.
Because when you substitute in,
Go ahead.
so then C becomes 0 and then K just becomes 1?
No, substitute in was right.
Yeah.
Look at how I started. I did B squared minus 4.
Oh, wait, is this the discriminant? Okay. And then times
What's A?
0.
No, what's A? What is it?
Wait,
K.
K.
What's C?
0.
No, look at
Wait.
C is there.
Yeah, but if you substituted it. Oh.
Again, what is C? What do you
Okay,
physically
4.
see? 4.
Okay.
K is a number. You have to be careful. Read what it says. For which values of K? K is a value. It's not an actual parameter. K is not your variable, is what I'm saying. K is a constant, right? These problems are traditional problems you're going to see, and these are useful even in calculus. You'll see stuff like this, okay, where the coefficients are not numbers, but they are what are called parameters, like A, B, C. A, B, C are not variables really, right? You know, A is a constant, B is a constant, C is a constant. They're all some number. K is some number also. Well, if we have a double root is only caused by a zero discriminant. So let's find the discriminant, b squared minus 4ac, and set that equal to 0. Set that equal to 0. Guys, this is not easy, so I really hope we're all paying attention right now. Some people seem distracted. This is not an easy topic, so I hope you're listening. 16k squared. Right, 16k squared shows up here. How do I solve this kind of a problem? I do two ways, two options. Which way do I want to do it?
Find the square root of all the numbers.
Yeah, I could square root everything or move this over and then square root it, right? Is that what you mean? Okay, you just can't just take the square root of the numbers right now. You can't do this. You just put a square root. You have to do some factoring to do that, right? What's the other way to solve this?
I have a question.
Okay.
Why wouldn't you add before K on like the second line?
Right here?
Yeah. Like
What's the formula for discriminant? B squared minus
Oh.
4
Makes,
times A times C. This is all multiplication here. So 4 times 4 is 16. K times K is K squared. So I can move the 16K squared over and then square root both sides, yes. Or,
Keep factor out.
yeah, nice. Factor 16 out of both terms, and you're going to get difference of two squares. Right? You can do it either way. Do it either way. Good, Eduardo, good. So I can take the 16 out, and either technique works, right? But sometimes people forget about the factoring techniques. I just want to point it out. And then this factors into difference of squares. 2 minus K and 2 plus K. And I like showing this because it's odd. People don't, not odd in that case, but peculiar. People don't like to factor difference of squares when it's a number minus a variable square. They don't see it, but it's the same thing, right? This is still difference of two squares. So we get K equals 2 and K equals negative 2. Now, had I done it the other way, I'm going to get the same answer. Let's do that in red over here. 64, move the 16k squared over. We can even divide by 16 actually to make it even easier to start. And then we'll square root it. And we get k equals plus or minus root 4, which is plus or minus 2. So the same answer either way we do it. The only reason I want to show you this, I'll point out, is because in parts B and C we're going to have to factor. We can't use the technique of moving it over. But this works for A for sure. But we will have to factor in parts B and C. Okay? All right, let's take a look at part B. Part B only changes because it says, now we want to look at when there are two different real roots. So who can tell me, when do we get two different real roots? When the discriminant is what kind of a number? When do we get two different real roots? Not imaginary, but real roots. When the discriminant is what kind of a number? So all numbers that are positive are greater than? Very good. This becomes a inequality. You see it? I know, this is weird. We're taking stuff from chapter 2, so I said it's not an easy topic. We're going back to chapter 2 and saying, when something is positive, it means it's greater than 0. Greater than 0 means I'm going to need to solve an inequality here. Well, the discriminant is the same thing still. It's still 64 minus 16k squared. It's no different than it was right here a minute ago. That was the discriminant a minute ago. It's not changing. So now we just have this instead. Again, it's the same thing as what was written in black. Instead of equals 0, in blue it says greater than 0. So I need to think of this as an inequality. How do I solve a quadratic inequality though? There's only one way we've learned to do this. A quadratic inequality. How is it solved, Mauro?
Well, you could just solve it as an equality and then use the
Solutions as the
critical point.
critical points. There they are. And we've always done it with factoring. So it's nice to see it done with factoring. But technically speaking, yeah, Mauro, you're right. You could have moved it over the way that Christian told us in red here. And gotten these, but you have to call them critical points now. Okay? Whenever it's an inequality, we think of it as an equation. but the solutions are not the answers, but critical points. We've done it with factoring every time, so I just wanted you to see it that way. And it's nice to test with factoring. It makes it easier. So I'm going to show the factored form of this again. 16, 2 minus k, 2 plus k is greater than 0. And then this means I have a number line, negative 2 and 2. I need to test my regions. So I take it and I plug it back into the factored form. Remember, it's easy to plug numbers back into the factored form. It always makes it a lot easier. So pick a number like 3 over here. 2 minus 3 is negative. 2 plus 3 is positive. A negative times a positive is negative. So let's put a negative in this region. I'm going to use yellow. I'll use yellow. Next, I take a number in this region. What's the easiest number in this region to test? Always. 0. 2 minus 0 is 2. 2 plus 0 is 2. Positive times positive is positive. Positive middle of the region. And you guys know enough already in this year to recognize that the next one is going to be negative for sure. Isabella.
So if you're substituting back into the factored form, you don't have to multiply it again by 16?
16 is positive. Is it going to change it?
No.
If 16 were negative, though, then would you have to multiply by 16? Absolutely.
So it's just like common sense.
It would be positive times positive, but then times the negative, and then it would take an effect, right? But if you factor out a positive, I'm not going to multiply by positive every time. It never changes the value. It's the negatives that matter. Notice that? If you have 2 negatives, you get a positive. If you have 1 negative, you get a negative. The amount of positives don't matter. Think about that logically in your mind right now, right? No matter what, I can multiply 37 numbers. The amount of positive numbers makes no difference. But if I get 2 negatives, the overall answer is positive. If I have 4 negatives, the overall answer is positive. But if I have an odd number of negatives, the overall answer is negative. So positives don't matter, which is interesting to think about. But that's a good point you're making. We want to know when the discriminant was greater than 0. Which region is greater than 0? Which region is greater than 0? The middle one. So our answer for part B is not k equals 2 and negative 2. It's that k is between negative 2 and 2. Here's my solution set for part B. Let me put a little, okay, part A is on the right, and part B is on the left. I don't even need to do part C. I don't even need to do it. What's the answer for part C? Let's see who knows what's going on here. Let's see who's picking up on context clues. You got it? First one.
Is it is it an or statement?
It is! Because part C asks us about imaginary roots. What do you know about the discriminant when the roots are imaginary? Answer that question first. Very good. So for part C, we are trying to figure out when the discriminant is less than 0. Well, that's pretty much taking this line. Let me point. Take a look up, please. This is the discriminant right here. And I want to know when it's less than 0. Well, that's this region and this region right here. I'm not going to redo the discriminant again, right? I'm not going to factor it out again and make another number line and do all this work again. It's the same discriminant. It's the same polynomial. It's the same quadratic, whatever word you want to use right now. So therefore, the number line schema, the way it's organized, negative, positive, negative, doesn't change. So if I want to know when the discriminant is negative, look for the regions of the number line you tested for part B, and you know it's these regions here. So k must be less than negative 2, or k is greater than positive 2. Now I did all of those in set notation. I could also write them in interval notation. Quickly, how would this one? I'm not going to write it, so listen carefully. How would this one appear in interval notation? Go ahead.
That would
Be specific.
Open parentheses, negative 2, comma, 2, close parentheses.
Very good. Open parentheses, negative 2, comma, 2, close parentheses. Meaning going from negative 2 up to positive 2, not including the endpoints. Upper one, in interval notation, part C. Something besides more, you got that one, I know that. Part C, interval notation. Come on. Yeah.
Open parentheses, negative infinity, comma, negative 2, close parentheses, and open the U thing. Open parentheses, 2, comma, infinity, close parentheses.
Very good. This one's a little tougher to listen at the same time, so I'll write it down just to be nice. Okay, and then it goes from 2 to infinity. Very good, Julia. Okay, and the other one was this, just because I'm writing it, I might as well. All right, those are interval notations. Again, recognize this is not a coordinate. It looks like a coordinate, right? You think of it as x, y. It's showing that it goes from -2 up to 2, not including the endpoints, parentheses. What if the endpoints were included, and these were closed circles and stuff, and this were a greater than or equal to symbol instead? How would this differ right here?
It'd be like
These would be brackets. Do we ever put brackets next to infinity? Because you can never get to infinity. It's never included. I don't even know the bells. It's an E with examine. It's a 41.
It's at 42.
40.
And what are we at now? 40?
No, we're at 39.
Okay, we got 2 minutes. Perfect. So let's quickly look at this one. This is pretty much what we did with numbers 1, 2, and 3. Determine what type of what type of zeros you have for the function, which means use the discriminant. And then use your calculator program, or go ahead and use your calculator to graph it, to verify. So this is just another example of 4 more practice examples for you guys to calculate the discriminant. So let's do that. B squared minus 4AC. That's going to be 25. That'll be a plus. 4 by 4 is 16. By 2 is 32. 25 and 32 is going to give me 37. 57. So there's my discriminant for the first one. And then all I'm asking you to do is find the roots with the program or by graphing and looking for the x-intercepts and make sure that it makes sense. So what would this graph look like? I have a positive discriminant, so I'm going to have 2 real, distinct roots. I know it's going to be a parabola. If I have 2 roots, that means how many x-intercepts am I going to have? 2. So it's going to be something like this. I don't know. I really don't know how steep it'll be. I don't know how wide it will be. It could go further down. We don't know. But it'll look something like that. Or maybe both roots will be positive, right? And it'll look like this instead. Maybe it'll look like this. Or maybe both roots will be negative, and it'll look like green. You see what I'm saying? It can be any of those 3 options for part A, if you use your calculator and look at it. If you go to your calculator and run the program, you'll just see that you'll get irrational roots. They'll be binomial conjugates. Yeah.
I just did part B on my calculator.
Yeah.
I got dot, dot, dot.
And you got dot, dot, dot.
I haven't got it yet.
I wonder why. Can somebody else try part B? Yes, your questions.
Oh, yeah. How come you didn't write like the square root?
Because the discriminant is the number under the root. It's
So
not
the
with the
root.
square root.
Okay.
And recognize that because in the last example, we did not say the square root of b squared minus 4ac equals 0, right? We said b squared minus 4ac equals 0. We didn't use the square root. That's a good point, guys. The square root does not get included when you're writing out the discriminant. Part B, did others get dot, dot, dot in the program? Yes? What the hell? What's the discriminant? What's the discriminant? Negative 71. So it must be only the case of irrational imaginary roots. Because 71 is not a perfect square, and it's imaginary. So maybe that's the only case that works with that. I don't know. But again, don't trust your calculator always, right? You see what I'm saying? You guys see what I'm saying, right? People say that all the time, oh, my calculator told me the answer. It's not always right. Later in the year, we're going to look at graphs that have holes in the graph. Holes don't appear in a graph in the calculator. And students are suddenly like bewildered. But my graph showed a continuous graph. There's actually a hole. It's a gap in the graph. We'll talk about that later in the year. Try the rest of these. Just write the discriminant, figure out what they are. Okay, for homework tonight. Do I see you guys tomorrow? Is it day 3?
Yeah.
I don't see you guys. So you have the weekend. So feel free to take the weekend and look at this. You can also, because you have the weekend, you can do the problem set in this section also. You want to get a head start and get a lot of extra practice. Do the homework and you can do the problem set this weekend. Might be a nice head start. Don't forget about your projects. Don't forget about the deadline for your projects. It is quickly approaching. Yeah, electronically, Google Drive. You can do your paragraph summary in the Excel file if you want. If you want Excel.
What is the deadline? When is the
It's on the 7th. First. Okay. Tomorrow.
We just need I did the numbers.
Don't forget your makeup test is due on Monday. I'll put that on homework. Sorry.
I did the numbers and the tables for the project. Is there a time that I can come to check if you finished?
Just look at freeze, okay? Doesn't matter. If I have a free and you have a free, it's easy. Okay, or during activities, times and stuff, it's fine. Once your numbers are right, you're right. You just have to give a quick summary. Like a 1-paragraph summary, that's all. Is that reasonable?